Okay, everyone. Now I'd like to return to that first problem where the energy of the particle is greater than the height of the barrier, and I'd like to calculate the probability that an incident particle is reflected and the probability that it's transmitted. Okay? It won't be too bad, but the technique that we're going to use, which will be to match up the wave function and its derivative at the interface, that's going to be new to most of us, all right? It's worth paying attention, though, and not just trying to memorize the answer, because we're going to use this same technique over again several times in our course. And if you go on to take the quantum mechanics course, well, of course, you'll see it again. So here, let's get started. Okay, so here's our problem once again. Okay, particle incident from the left encounters our boundary. The energy of the particle is greater than the height of the barrier. And we know that we can describe the particle in region 1 with this wave function, psi1 equals a e to the I k1x plus b e to the minus I k1x. And in region 2, we can describe it this way. Okay? So, if you like, that's a general solution to our problem. But now we're going to use the boundary conditions to find the specific solution or particular solution. So let's see what the boundary conditions are. Well, the first is that the wave function at psi equals zero, x equals 0 must be continuous. And we know this is true because if the wave function were discontinuous, then there would be a point where the wave function suddenly changes, where we would have two values of the wave function at one location. That doesn't make any sense. The second boundary condition is that the first derivative of the wave function with respect to x that must be continuous also. All right? And that turns out to be related to the idea that only finite forces can act in our system. Okay, in any event, those are our boundary conditions. So let's see what happens when we impose them on our general wave function above. So looking at boundary condition 1, this tells me that at x equals 0, psi1 must equal to psi2, so that a e to the I k x, but x is 0, plus b e to the I times 0 must equal c times e to the I times 0. All right? Okay, well, e to the I times 0 is 1, so this simply means that a plus b equals c. Okay? So we've used the first boundary condition to see that there's a relationship between the amplitudes, A, B, and C. They're not all independent. Here, let's look at boundary condition 2. So coming back to the wave function we've written down here, we have to take its first spatial derivative on the right side and on the left side in order to impose this boundary condition. So the first spatial derivative of a e to the I kx is I times k1 times a e to the I kx, but x is 0. And then we have the second term, b e to the minus I kx. When we take the derivative of that, we get I times K1, and then B times e to the I kx. On the other side, we have C I e to the I k2x, and we get I k2 times C e to the power 0. Simplifying this, we find that K1 times A minus B is equal to K2 times C. Okay? That's our second equation. All right? And now what we're going to do is to solve these two equations simultaneously to find B and C in terms of A. Okay? Here, let's do this. Let's find the reflection coefficient, little r equals B over A. So to do this, we'd like to combine these equations to eliminate C. And we can do that by substituting the first equation into the second one, so that we have K1 A minus B is equal to K2 times C, which is A plus B. And now let's solve for B in terms of A, okay? So separating the terms, we have K1 times A minus K2 times A is equal to K1 times B plus K2 times B, okay? Or A times K1 minus K2 is equal to B times K1 plus K2. Or now, solving for B in terms of A, we get B is equal to K1 minus K2 divided by K1 plus K2 times A, okay? Or if you like, B over A, the reflection coefficient, is equal to K1 minus K2 divided by K1 plus K2. Okay, that wasn't so bad, was it? All right, so we can use what we know, we can use what we found to find the reflection coefficient for amplitude. And then from that, we can find the reflection probability. So the probability of reflection is given by the absolute value of R squared. And so that's equal to absolute value squared of K1 minus K2 over K1 plus K2. There we go. For a particular problem, knowing the energy and the height of the step, we can find K1 and K2, and then we can figure out the reflection probability. Okay? Well, the second thing we can find is the transmission probability. Let's see. As I mentioned, the transmission probability is just 1 minus R, because if particles aren't reflected, then they're transmitted. And so this would be, well, 1 minus R, and then we can use R from the previous expression. All right. In fact, I won't simplify this anymore. A related question would be to find the transmission coefficient for amplitude. That is the relative amplitude of the transmitted wave divided by that of the incident waves. That's, excuse me, little t, which is c divided by a. Okay? And with a little bit of math, we can figure this out as well. All right? And it's straightforward to show that c over a is equal to 2k2 over k1 plus k2. All right, let's stop here.